In control systems, many real-life engineering systems can be modeled using mathematical equations. One common model is the second-order system, which is widely used in electrical, mechanical, and biomedical signals. In this video, we will analyze the response of the second-order control system when a unit step input is applied. We will determine 4 important transient response characteristics, which is the rise time, peak time, settling time, and maximum overshoot.
A second-order system is a system whose behavior is determined by 2 energy-storing elements. Because of this, the system's output depends on 2 dynamic factors, which makes its response more complex than the first-order system. Second-order systems are very common in engineering. For example, they appear in spring mass mechanical systems, RLC electrical circuits, and many feedback control systems. These systems can sometimes oscillate or overshoot before settling to their final value. The transient response refers to the temporary behavior of the system immediately after an input is applied. It describes how output changes from its initial condition until it reaches a steady and stable value. So, a second-order system describes the type of system, while the transient response describes how the system behaves before it settles.
Alright, I'm Victor Bedasi, and I'm a member of Group 1. So we are being tasked to solve this particular question under the course classical control system. So the question is, when a second order control system is subjected to a unit step input, the values of zeta is given as 0.5 and that of omega n, which is the natural frequency, is given at 6 rad per second. So we have to determine the rise time, the peak time, settling time, and the peak overshoot. So I'll be solving the rise time, and my friends will take us from there. So in finding for the rise time, which is normally represented as T of R, we need 3 key equations, which is this main equation. We have pi minus 5, all divided by, that's TR equals pi minus 5 divided by omega d, which is the damping frequency. Then this phi is given us, in order for us to get phi, we are going to use this equation, phi being equal to tan inverse of the expression root of 1 minus zeta squared divided by zeta. Then we have to find this parameter as well, since it has not been given in the question. So the damping frequency omega d is given as omega n root of 1 minus zeta squared. Alright, so we are going to need just this 3 equations in solving. So the rise time T of R is given as pi minus this equation, which is tan inverse of root of 1 minus zeta squared over zeta, all divided by omega n root of 1 minus zeta squared. Right. So we have been given zeta in the question to be 0.5, and we have been given omega n, which is the natural frequency, to be 6 rad per second. So we are just going to substitute these values into our equation to find our rise time. So we have pi minus tan inverse of the root of 1 minus zeta is given as 0.5. And we are finding zeta squared. 0.5 squared is 0.25. All divided by 0.5. Right. And this is divided by omega n, which is 6, multiplying the root of 1 minus zeta squared. And we know zeta is 0.5. So that one square will give us 0.25. So if we evaluate this section, we are going to get 60. That's the tan inverse of this. If we use the calculator, but for the sake of time, we'll write that straight away. So if we evaluate that, we are going to get 60. But we are working with in radian, but not degrees. So for that reason, we are going to change that 60 to radian. So we are going to have pi minus pi on 3. That's 60 in radian is pi on 3 divided by 6 by this. If we value this, we are going to get 5.19, right? So we know the value of pi to be approximately 3.142 minus, if we break this one down, we are going to get approximately 1.047, all divided by 5.19. If we break this down further, we are going to have our rise time to be 0.404.
Your system is subjected to a unit step input. The values of zeta, which is the damping ratio, is 0.5, and the undamped natural frequency is 6 rad per second. Determine the rise time, peak time, settling time, and peak overshoot. I will be taking you through peak time. So let's move on to our workspace. So from the question, we have our zeta, which is the damping ratio. To be 0.5, and omega n, which is the undamped natural frequency, to be 6 rad per second. As I said, we are dealing with peak time, TP, and TP is equal to pi over omega d, where omega d is the damped frequency. But in this question, we only had omega n, the undamped natural frequency. But omega d is equal to omega n multiplying square root of 1 minus zeta squared. So from that, we can input equation 2 into equation 1. So we can have Tp equal to pi on omega n square root of 1 minus zeta squared. So now we can do our substitutions. We have pi, we have omega n to be 6 rad per second, multiplying the square root of 1 minus the damping ratio squared, which is 0.5 squared. So pi on 6, 1 minus 0.25. This gives us pi on 6 multiplying square root of 0.75. So we can use our calculator to compute this, and we are getting my calculator. So So we have pi on 6 multiplying the square root of 0.75. We have 0.604599, which is approximately 0.605 seconds. So our second order control system uses 0.605 seconds to get to the first, or usually the maximum peak value.
My name is Nana, then I'll be talking about rise time. So rise time is a time domain performance parameter in control systems. So it deals with the time required for a system output to rise from a small percentage of its final value to a larger percentage after a step input is applied. So the importance of this is because it indicates how quickly a system responds to an input signal. Some examples of its engineering applications are motor speed control, robotic positioning, aircraft autopilot systems, and biomedical devices like infusion pumps. So knowing the rise time helps engineers to evaluate system responsiveness and stability. Also, if the rise time is very high, the system responds slowly, which can lead to delays or poor performance. On the other hand, if the rise time is very low, the system responds very quickly but may experience overshoot or oscillations, which can reduce stability. The rise time is an important parameter in control system design because it helps engineers to balance speed of response time with system stability and accuracy.
So my name is Jafet Achimbe, and I'll be speaking about the peak time. The peak time is the maximum value a system reaches when it's applied to an input signal. Right. So the maximum value that the system reaches when the signal is applied to it. So the peak time is given by 3P is equal to pi over WD, where WD is given as the damp frequency. So my friend has already given the expression for WD right here. So let's say for instance, we are finding for TP. So TP, there's the expression for TP, right? So we use this expression to find for WD. So when we get the WD, bring the damp frequency, we place it here. So the value, let's say you solve this right. So let's say the answer you get for TP. When TP is in TP, the answer is empty large. That means the system's response will be slower, right? But when the TP answer is small, the system response will be faster. So that's basically everything about the TP. So the TP is just the system's maximum value that it reaches when it's applied to an input signal.
My name is Gaspar Africa, and then I'll be explaining settling time. So settling time is the time a system takes to become steady after there is a change in input. So the settling time determines how fast a system becomes stable or it stabilizes when there is a change in input. Application of settling time. We have temperature control and then medical devices. And the effect of settling time. High settling time determines that the system stabilizes slowly, and then low settling time determines that there is fast stabilization in the system.
Okay, I'm Cherma Dimantini, and I'll be taking you through the settling time, which is mostly represented by TF. And then for the settling time, we have a lot of criteria. That's the plus or minus 2% or plus or minus 5%. But mostly for engineers, we mostly use the plus or minus 2%. So for that, our settling time uses the formula 4 over the damping ratio times the natural frequency. And from the question, they already gave us the parameter for the damping ratio and the natural frequency. So when we substitute our parameters, our settling time becomes 4 over 0.5 times 6, which will be 4/3. And then when you just want this into the calculator, we get it to be 1.33 seconds. So yes, this is our settling time. And then from the equation, realize that the larger the damping ratio, the faster like the system will settle quickly. And then if it's like lower, that means there will be a longer oxidation. Yes.
The maximum overshoot refers to how much the output of a system exceeds the final stated value during the first peak. And mostly this is expressed as a percentage of the final value, right? So when there is a higher overshoot, it means that the system now oscillates more before it stabilizes.
So please, I'll be taking you through the last question, that is finding the maximum output. And with finding the maximum output, we have a formula, that is MP is equal to E raised to the power minus pi zeta over square root of 1 minus zeta squared times 100. Zeta is the damping ratio, and with this question, zeta was given as 0.5. So as you can see, we fixed it, the 0.5 into the formula, where we got our answer to be 16.3%. This means that the system output can exceed to a final steady state of about 16.3% before finally settling back to its stable value. In conclusion, we have discussed and analyzed time response characteristics of second order control systems, including peak time, rise time, settling time, and maximum output. These parameters enable engineers to be able to evaluate how fast and how stable a control system responds to an input.